Hello and welcome to your 10th lecture in Earth Sciences. This is Dr. Hurt. We're going to be going over today mass wasting and soils. So we have our lecture assignment. Hope you got your lecture assignment packet. I got mine right here, and we'll be going over everything that's in there. So right here, without further ado, we'll get started. So if you look right here, this is a photo from my time in Peace Corps in Malawi. So this is actually a bridge. What you're looking at here is actually a bridge that had just fallen, just caved in. And it was kind of interesting because right before this bridge had fallen, literally the day before, I had taken a group of farmers down here and was showing them how kind of, I don't know what you could say, not great farming practices were contributing to soil erosion along the banks of this river. And I was actually, it was crazy because the same day I was explaining to people about how, they're really putting this bridge in danger from soil erosion. The very next day it broke, and there's a thunderstorm that day. The banks of the river eroded. And you can see this is the wreckage of the bridge, and this was the nicest bridge in town. I'm sorry to say. So it was really a tragedy. It fell over like this. But anyway, that is kind of what we're talking about today. We're talking about mass wasting, and we're talking about soil and soil erosion and things like that. So first of all, what is mass wasting anyway? What does that even refer to? Mass wasting is maybe colloquially, you might have heard things like landslides and stuff like that. That is a form of mass wasting. Mass wasting is just, well, you see the definition right up there on the screen. It's the downhill movement of rocks, sediment, soil under the force of gravity, okay? And it could be something really dramatic, like what you see in the slide right there with this tremendous landslide, right? Or it could be something that's actually pretty slow. But at the end of it, the end of the day, it's just the downhill movement of soil particles and sediment, all this under the force of gravity. Okay. One big concept that comes up with mass wasting is this other concept of the angle of repose. So, kind of mentioned this a little bit in previous lectures. But the angle of repose, you see the definition up there, but it's the angle of, it's the natural maximum angle at which sediment particles of a given size are at rest before they begin to slide under the force of gravity. So if you start to pour sand into a pile, or coarse sand or pebbles or whatever, they're going to form a cone shape, as you know. They're going to form kind of a slope, and that slope is going to change in its angle under a bunch of different characteristics can change the angle of that slope. But once it exceeds that slope, you're going to start to get the downhill movement of material downslope. Okay, once it exceeds the angle of repose, that's when mass wasting starts to occur. So it says right there, mass wasting occurs once a slope exceeds its angle of repose. You could see a beautiful angle of repose right there in Talus Slope. This is looking out over Jackson Hole, Wyoming, and there's a beautiful Talus Slope in the Grand Tetons, and you can see also cinder cones. Cinder cones are like little volcanoes made of cinders, made of little pieces of volcanic rock. You can really get a good idea of angle of repose from there. So some of the things that can kind of increase or decrease angle of repose. I don't think I have it. Oh, I can have a little bit right here. So coarser sediment usually has a steeper angle of repose, whereas finer sediment usually has kind of a shallower angle. Another thing that can affect it is the angularity of the material. So you could see like the more irregular kind of angular pebbles or gravel or whatever can have a steeper angle versus something smooth. Smoothed out will have a lower angle of repose. Water also plays a difference here too, and we'll talk a little bit about the role of water as we move forward. But water is actually kind of complex. It can either increase the angle of repose or decrease it depending on how much water is involved. So water plays a role here, but the role of water is complex, and we'll talk about that as we move forward. Okay. So anyway, let's talk about different kinds of mass wasting. So here's a little graph that's going to kind of guide our discussion here. And it's showing different types of mass wasting depending on the conditions. Some of them are slow, some of them are fast, some of them are also wet, and some of them are dry. So you can see the dry conditions are near the bottom, wet conditions are near the top, slow condition, or not, I shouldn't say conditions, but slow kinds of movement are to the left, faster kinds are to the right. Pardon me. So I'm just going to go through a few examples of these things, and you can kind of get an idea how some of this stuff works. Sorry, I'm just kind of realizing the lecture's not updated, but here I have the correct one up here now. So anyway, so that's the angular post. Yeah, we're going to go over these different kinds of well, first I want to kind of go over kind of three main categories of mass wasting. So we want to go over these three kind of broad categories. Okay, this is the kind of movement that we see within the mass wasting event. So first one here is a flow. So I'm going to show these kind of three animations, and hopefully you can kind of conceptually understand each of these three categories. Okay, so first of all, with a flow, I'm going to show the flow happening. Okay, so there's the flow. Let me show it again. Notice that in the flow, so we have this, like, I don't know what you call it, hillside or talus slope or whatever. Notice that all the particles are going to all move kind of separately. So every particle is kind of like on its own path, and it's moving willy-nilly downhill on its own particular pathway. Okay, so all the particles move separately. Examples of this are things like soil creep, debris flows, earth flows, mud flows. Okay, so you could see soil creep, earth flows, mud flows, debris flows. Okay, so those are things that are rather, you'll notice for the most part, not soil creep, but for the most part the other things are all relatively wet conditions. Okay, so they're things that are happening under the influence of water. Okay, so the next thing is a slide. Now in a slide, what happens is like a coherent block of whatever it is, soil or rock or sediment or whatever it is, it's going to slide downhill. Okay, so a coherent block is going to slide downhill together. So things like slumps or rock falls, or not rock falls, but rock slides actually are good examples of this, or debris slides. Okay, so you can see here a slump. I hope you can kind of see in this picture how the slump, there's like a coherent block of material that stays intact and it slides downhill. Same thing here with the debris slide. Okay, so we'll cover more of that a little bit later. Last thing is then a fall. So a fall is when free, loose material falls directly under the force of gravity from like a sheer cliff face. An example of that is a rock fall. Okay, I don't think we have any other examples of falls here, no. So it's just rock falls. Okay, so those are the three broadest kind of categories of mass wasting. Some of these, like I said, are fast. Some of these are slow. So we'll go through some of these one by one. We're not going to go through all of them, but we'll just kind of explain some of these and give you a flavor for it. On the test, I just want you to make sure that you kind of familiarize yourself with at least two of these, maybe like one fast one and one slow one, and make sure that you're able to kind of explain that example, like one of these specific processes, a rock fall, a debris slide, a debris flow, a soil creep, whatever it is. Just make sure you're able to explain it and give me some examples. So we'll do a rock fall first. So they're easiest to understand. There's not really very much mystery to them. It's just when under the force of gravity, rocks and debris fall off of like sheer cliffs, steep cliffs, rock walls, and they come to rest in a talus slope. Okay, so something like this is a good example of pretty terrifying, but it's a good example of a rock fall. Okay, so there's There's a rock fall for you. Okay. All right, so let's go take a look at some of these flows. Now remember, flows are different than the slides because with flows, the particles are basically following their own path. They're not staying together in a coherent block. They're all going to, follow their own path. The difference between like mud flows, debris flows, earth flows are fairly small. So I don't make like distinctions among them. But they do kind of differ in the speed at which they happen and the conditions of wet or dryness, the moisture content. But you don't have to make distinctions. So we'll just kind of treat them all together: debris flows, earth flows, and mud flows. These are things that occur usually under wet conditions, like I said. So they include wet mud, boulders, trees, whatever soil, and it's all going to move downhill usually after a heavy rainfall. So the difference between these things, like I said, kind of depends on the sorting and the size of the particles. It depends on different different conditions of how much water was involved, how fast it is. So like I said, you don't have to make these subtle distinctions. But anyway, one thing I kind of want to show you in this picture is that under dry conditions, you can see that all the sediment is relatively stable because the particles of the sediment are all kind of touching each other and they're in contact with each other. But when it gets water saturated, the hydraulic pressure, the water pressure in the soil builds up so much that it literally pushes the particles apart and separates them, and they lose contact with each other. So I hope that you can see in that diagram right here, the particles have lost contact. And once they lose contact, they're able to slide downhill because they lose what's called shear strength. They can be easily sheared. That means easily move side by side. And it starts just free flowing downhill. Okay, so like I said, usually after a heavy rainfall, the pore space between sediment grains fills with water. The rise in hydraulic pressure in the pore space causes individual sediment grains to lose contact. That loss of internal strength leads to the failure of the slope. One really famous example of this of course, I grew up in Southern California, and one really dramatic example of this was 2005, which was, by the way, an El Nino year. There was a lot of rainfall in California that year. And this was a terrible debris flow that destroyed this town of La Conchita in Southern California. So here's a little video just kind of showing you what's going on there. Very dramatic. Let me actually I forgot the sound is not on here. Let me turn that on a little bit. Sorry. Here we go. And you have to remember, this is 2005, so this is kind of before the time of smartphones and people, when they were recording things, they had like a camcorder or something, so the video quality is not as so good, but you'll get the idea.
It took 15 seconds for the Earth to swallow the heart of La Conchita. In January 2005, a 100-year storm, 26 inches of rain in 16 days, unloosed the hillside. Then, Mike Bell remembers, a mountain of earth descended on the town.
It just breaks our heart for the people in Washington. We absolutely understand how helpless you feel, knowing that relatives and friends can be buried up there, and you don't know where they are.
The La Conchita slide stopped at Ernie Garcia's house. And that's your house?
Yeah.
Right there.
Yeah. And this one here, right across the street is this one here.
So really that one is crushed here. These are gone.
Yeah. These are gone. This one here, and this one here. See this?
Anyway, I think you get the idea, but it was quite a dramatic event. It was a big deal in Southern California when this all happened. So, like I said, water plays kind of a complex role in mass wastings and angle of repose. If you have dry material like this dry sand, you can have a relatively stable hillside. Sometimes, though, a little water can actually help to bind the grains together. So, there's a certain cohesive force that's exerted by the water. If there's a thin film of water on the grains, it actually helps the grains bind together. So you see this really clearly with a sandcastle, right? Obviously, to make a sandcastle, you need a little bit of moisture for the sand. You can't make a sandcastle with dry sand, but you also can't make a sandcastle with sopping wet saturated sand too, right? If the sand particles lose contact with each other and water fills up that pore space, it loses all internal strength and it just turns into like a big muddy soup, right? So you all know that, I'm sure, from making sandcastles, and I'm sure most of you being from Corpus Christi, you not from Corpus Christi, but living here, you've made sandcastles and you had this experience. So anyway, let's see. Moving on to that, we want to cover some of these other things like going on to slides. So slides are slumping and debris slides. So we'll talk about slumps and debris slides separately. They are significantly different. So debris slides are a type of landslides, okay? And by the way, this term we use a lot, landslide, is not really a kind of a scientific term. So it's maybe the closest thing to a landslide is it's really what you're talking about is we usually call it a debris slide. But anyway, it's a mix of mass, rocks, regolith, soil that flows downhill on a cushion of air. And I really shouldn't put flows, but really slides downhill. So it's caused by a slope failure along a flat plane roughly parallel to the slope, detachment of that. So I'll explain what that means in just a minute. One really famous example of a debris slide was in 1959, August 17th, there was a massive debris slide in Montana triggered by a 7.1 earthquake. It caused the failure of the slope. You can see here, this is the slope right here. I hope you all can see that in the picture. It's a huge, huge, huge area that failed and slid. And what it actually did is it choked the Madison River, the Madison River Canyon, and it created a lake. So this lake that you see right here did not used to exist until it was choked. The river was choked by the landslide, by the debris slide. And it created a lake. After the earthquake, it was called Quake Lake, right? So it gives you an example. So this is kind of what I was talking about, that there's a slope failure along flat plains parallel to the slope. This happens a lot. That we talked about sedimentary rocks, and we talked about how sedimentary rocks have bedding planes, right? So this can happen where you have sedimentary rocks, you have the bedding planes, and those rocks happen to have been tilted so that the bedding planes are roughly parallel to the slope. So you could see here's the angle of the slope going downhill. Here are the bedding planes. You see the bedding planes. And the bedding planes are all parallel to the slope, right? So what happens is it's really easy for these coherent blocks to slide downhill, okay? To just detach and slide downhill under the force of gravity. So that's what we mean when we talk about slides. Remember, slides have that coherent block of material that stays together, okay? A lot of times these things are actually traveling at very high speed. And the reason that they're able to travel at a very high speed is something you probably are familiar with. So you can see this in this little video right here down below. You can see these cars hydroplaning, right? And you know that, especially I'm sure this happens in Corpus Christi a lot, where you get a little bit of water on the road and you can lose control really easily. Why? Because your tires are no longer touching the road. They've lost contact with the road and they're kind of riding on a cushion of water. And the same thing can happen with rocks, right? During a slide, the rocks can actually lose contact with the surface below. They're riding on a cushion of air. It allows them to move at really high rate because they have basically no friction, right? They're just sliding straight down this friction-free surface, riding on a cushion of air or water. Same thing, by the way, happens with avalanches. The snow that moves downhill during an avalanche is usually similarly riding on a cushion of air, and it really allows the snow to move very quickly downhill. Okay, so here's a good example of a debris slide. You can see how the material kind of stays together as a coherent block. You can actually see the bedding planes pretty well, and you can see how the bedding planes again are parallel to the slope, and that's when you really have prime conditions for a debris slide like that. Okay, this is a really striking example of a debris slide in Norway. And again, I love this video not only because it's really cool video, but it also shows how, again, the land stays in a coherent block. So take a look at this. This is a landslide. Oh, it's really a debris slide. The earth is sliding into the ocean here. And you see how this is moving as one coherent block, right? It's moving together as one block of material. So there you have it. It's a pretty striking video. Another thing I want to talk about now is slumping. Now, slumping is a type of slide, but it's happening much more slowly, so it's not such a dramatic event. I actually notice a lot of slumping occur here in Corpus Christi. You'll actually see this if you start keeping your eyes open and looking like in our drainage channels and things like that, and little streams that run through the city. There's like little drainage streams that sometimes only have water in them during a storm, but you'll see slumping along those drainage channels a lot. So slumping occurs when, again, a coherent mass of the land starts to just slowly slide downhill, and it leaves these scarps like this, and you'll see these kind of like almost look like steps of land, right? So something like this is a good example. I could have taken this picture in Corpus. I see examples like this all along those stream channels I've already talked about. Okay, so here's a good example of slumping, right? That's showing slumping. Of course, that's just like a sand model, but it still kind of gives you an idea. Okay, now we're going to talk about some of these slow processes. So these are things that, again, not very dramatic, but they happen all the time. One of these is soil creep. Soil creep is when soil very slowly moves downhill. And what is powering it are cycles of contraction and expansion of the soil. There are a few ways that you can get those cycles of expansion and contraction. So one way is when you have expansive clays. That's the main way that you have them here in Corpus Christi. You can get soil creep. Now, one thing I want to emphasize is that you're only going to get these kind of mass wasting processes on hillsides. Do we have a lot of hills here in Corpus Christi? Not many, right? It's a very flat place. So you're really only going to see this. Sometimes I get like earth observations from people saying, "Oh, I found soil creep," and it's like I'm looking at the picture and it's a totally flat surface, and I'm like, well, you're not going to get any kind of mass wasting on a totally flat surface. You have to have some kind of a hillside there. So when you see soil creep happening, it's going to make things like this. If you ever see like fence posts leaning over to the side, again, this is what I mean. Like people will find fence posts leaning over and they'll think, oh, this is soil creep, but it's totally flat surface. No, you have to have some kind of hillside for this. Another really telltale sign of soil creep is this. When you get these J-shaped curved trunks and trees on hillsides, it's a very clear indication of soil creep, very reliable indication of soil creep. The trees are bent because they keep leaning over and then trying to right themselves up. So they lean over and they try to right themselves up again. right? And they end up with that bent trunk. So soil creep happens when you have expansive soils, like we do here in Corpus Christi. We have expansive soils. We'll talk more about that later. It's due to the clay content of the soil. You also get it up north where you have freeze-thaw cycles. So, the soil freezes and it expands because of the water content, and then it contracts when it thaws, and then it expands again when it freezes. And then, so you get those freeze-thaw cycles, expansion, contraction, expansion, contraction. That's what causes soil creep. Okay. So, I think we got everything done with mass wasting. Do want to move on now to soils. So, with soils, okay. Whoops. Zoomed out. I'm sorry. How do I get back? No, okay. I'm sorry. Screwed that up a little bit. With soils, okay, so soils are made of a few different things. So when we use the word soil, it's a collection of basically four things. First thing here is, of course, the mineral content. So the mineral content is all the sand and and clay and silt and whatever of minerals and broken rocks and things like that are composing the soil. Okay, so that's part of it. But you can see that's only really about 50% of the soil. The other part of it is air. So that's an important component of it too, and I'll explain more about why that's important as well. So there's pore space, there's open space, there's some space for air in there. Another part of the soil is the water. Okay. And that's also important, as you can imagine, for fertility of the soil as well. And the last bit is OM. OM stands for organic matter. Okay, so soils, unlike just a pure mixture, not just a pure mixture of sand and clay, they have organic matter in it. That could be more or less. So there's a difference between soil and what's called a regolith. So we actually make a distinction between those two things. Regolith is just a pure mixture of broken down rocks and minerals, okay? Like a talus slope, loose sand, loose gravel, things like that. That would be regolith. On other planets, or on the moon, the sediment that covers those planets, we call that regolith. We don't call that soil. One of the key ingredients that's missing here is the organic matter. You have to have organic matter to be a soil. Okay, otherwise you're a regolith. All right, now we also talk a lot about something called soil texture. So soil texture refers to the proportion of different particle sizes. Again, so many people get this mixed up, and they think as soon as they hear texture, they think rough and smooth. Rough and smooth have nothing to do with this at all. Rough and smooth just get that out of your mind, okay? Whenever you hear texture in earth science, we're talking about the distribution of different particle sizes, okay? Now, in soil texture, we're talking about the distribution of 3 end-member particles. Sand, the largest one, silt, and clay, all right? Now, sand has some good things about it, but it also has some drawbacks when we talk about fertility of the soil, okay? A lot of times when in soil, we're interested in the fertility of the soil, right? How good is it at supporting vegetation, right? So sand, you know that sand isn't really great for supporting plant life, right? What's the problem with it? Well, it drains too quickly. Water just drains right through it. So it doesn't hold water very well. It's also very difficult to extract nutrients out of the sand. Clay, on the other hand, is also not ideal for supporting plant life. There's so little pore space. The soil gets very heavy. It captures water well. It also has a lot of nutrients available. However, there's very little pore space available for air, for the roots. So it makes a lot of problems in supporting plant life as well. Silt is pretty good, But the best is when you combine these different soil textures to come up with something called loam. Loam right here in the center is actually the most fertile type of soil. Okay, so you can see that it is kind of halfway between sand and silt, and it has a little bit of clay, but not a lot of clay. Pure clay would be up here at this point. Pure sand would be over here at this corner, and pure silt would be at this corner. Loam is kind of in the middle, but further away from the sand or from the clay side of things. Okay, so it just has a little bit of clay. So the best texture to support plant life is loam. Okay, that's the most ideal texture, generally speaking. Now, soils need to have air, right? That's shown in the white, and it needs to have the water, right? Plant roots, here are the roots, need both air and water. Just like you and I, plants need air to survive. The roots are no different. Roots require air. If they don't have air, they drown and they die. So that's why, for example, you can't just take a plant and stick the roots in water and the plant survives. Some plants obviously do because they're aquatic and they're designed that way, but most plants don't because they need to have air. They literally drown when you stick them just in water. Okay, so they need to have some kind of air pockets inside of that soil. All right, we're going to go on to a new topic here. It's called cation exchange capacity, CEC. And again, it gets back to this idea that, plants need nutrients to survive, just like you and I. There are certain minerals and elements that they need, just like you and I need. And they're going to get those a lot of times from the soil, right? They're going to extract it from the soil. So just like any living thing, plants need nutrients. Especially what they need are calcium, potassium, magnesium, and sodium. Okay, so those are the things that they need from the soil, among other stuff. Plants cannot produce their own calcium, potassium, magnesium, and sodium. But what they can produce is hydrogen ion. Okay, hydrogen ion, which by the way is acid. Okay, so they can produce organic acids. So what plants do is they actually exchange the hydrogen cation, the acid, the hydrogen cation with those other cations. So they do a flip-flop. They trade from the soil to themselves. So you can see here's a plant, right? Here are the roots of that plant extending all over through the soil. It produces hydrogen ion, which we learned in the last lecture, right? I mentioned how a lot of plants and lichens and fungus produce organic acids. And why do they do that? This is part of weathering, right? The reason that they do that is so that they can exchange cations with the soil or whatever substrate they're surviving on. So what they're going to do is they need the calcium and the potassium and the magnesium and sodium. So what they're going to do is they're going to trade. They're going to trade those ions with the soil for their organic acids. And it'll actually kind of acidify the soil, right? So a lot of plants actually can acidify soils. So let's talk a little bit more exact. So the capacity of a soil to exchange cations is called cation exchange capacity, and it is a very important aspect in the fertility of that soil. Okay, volcanic soils are really good they have a very high cation exchange capacity. It's one of the reasons that volcanic soils make really super rich, super fertile soils. Okay. All right, so let's move on a little bit to what are called soil horizons. So maybe you have noticed this before. Maybe you're looking at like an exposed hillside or something. You might notice kind of like different colors in the soil horizon, the exposed soil. Or maybe you're digging like a fence post or something like that, or whatever, and you notice there are like different colors in the soil as you go down different depths. So this is kind of a idealized situation. Not all soils, and there's many different kinds of soils. That's actually part of your reading assignment, is to go and look at the different kinds of soils and try to identify which ones are in Corpus Christi. But this is kind of an idealized situation that shows a soil with all the different kinds of horizons. Not all soils will have every kind of horizon, but I want to kind of walk you through some of the different common what are called layer horizons, but maybe you could think of them as layers that are in a soil. Okay, so the first one we'll talk about here is called the O horizon. O is the top, and it stands for organic. This is the layer that is most fertile, and it contains a lot of organic matter, what is otherwise called humus, and that is the most nutrient-rich horizon. That's the horizon that's going to support all the plant life. Okay, so the plant roots are going to be very thick in the O horizon as they extract nutrients. The one below that is called A. A is right below O, and it has a mixture of humus and mineral grains, so it's not as rich, but it's still a soil, and it still contains a lot of organic matter. Now, kind of superimposed over OABC, okay? So there's this thing we call the E horizon. E stands for alluviation. And alluviation, what alluviation refers to is that as water from the surface percolates down, it's going to pick up a lot of nutrients. And as it percolates down, it's going to pick up different cations, different water-soluble cations, and it's going to leach them down deeper and deeper and deeper into the soils, okay? Some places that happens in a very strong way, some places that hardly happens at all. So actually, you see in this picture, I don't have an E horizon, and it's complicated because the E horizon, if it exists, can be superimposed over like ABC, or it can go down just AB, or whatever. You know, it just depends what it is. But I just want you to be aware that it exists. It stands for alluviation. Water leaches through the topsoil, leaches out, dissolves out the nutrients, and translocates them. That means moves them into deeper layers of the soil. Now the B layer, which is below the A layer, contains some organic matter. A lot of that material has been translocated by alluviation. It has a lot of clay that has been translocated due to alluviation, and it's often called the subsoil. So it's clay rich. It often does have a lot of nutrients in it, but it doesn't have very much organic matter. It's almost totally depleted in organic matter, and therefore it's not going to support a lot of plant life. Below that is the C layer. This contains little nutrients. It contains no organic matter, and it's mostly regolith. And you can see that in this depiction. You see the plant roots don't even bother with the C layer. They don't go down into it because it doesn't provide very much for them. You know, maybe water, but it doesn't have very many nutrients, and it's of little use to it. Okay, so those are the different layers you should have some familiarity with. Now, going into how soils are formed, there are 5 factors that are important for soil formation. You know, first of all, soil formation, one of the first factors you see up here is time. It just takes a long time to create a soil. Some places it takes 1,000 years to create 1 inch of topsoil. And that's really staggering. You think about it. That's why topsoil loss is a big deal in a lot of places. That topsoil is so important. The O layer, right, is so important for sustaining crops, and yet it's built up very slowly. So it's very important to retain topsoils. Okay, so time is an important factor here. The parent material is important. You know, what is the regolith composed of? Is it composed of limestone or granite? You know, volcanic material? That all makes a difference in terms of the what kind of soil you end up with. The climate makes a difference. How much rainfall you get. whether it's an arid desert environment or a rainforest environment, you're going to create very different kind of soils. The plants and animals that are present, if you have a rainforest, that's going to contribute a lot of vegetation, a lot of organic matter, versus if you have a desert where you have very little organic matter being added to the soil. There's very little plant and animal life. The topography makes a difference. The steepness of the slope, right? If you're in a flat area, your soils are going to be really thick. But if you're in a slope, a hillside, most of that material is going to mass wasting, right? It's going to move downhill. So you're going to get very little soil and regolith buildup on a hillside. So that makes a difference as well. And time, I already discussed, okay? There are actually 12 main types of soil. Those are things that you have to read about in your book and try to look at this map and identify, where, what kind of soil are we going to have, here in Corpus Christi, and why is that important? So anyway, soil erosion. I want to talk a little bit about soil erosion. I started with a picture from Malawi. Here's another picture there. This is their main highway, just totally taken out by. You can actually see the rushing water right here, but totally taken out by. This is a pipe that's going underneath there, a storm channel, and it got totally taken out by erosion. Right, I already showed you these pictures of the erosion that took place there. Took out that bridge. So soil erosion is a big problem, right? Soil erosion can create big problems for crops, right? It can destroy crops, destroy farmland. It can erode topsoil, right? Remove topsoil that contains all the fertile nutrients, things like that. So what are some ways that we can combat soil erosion? What are some farming or agricultural techniques? One of them are contour rows. So contour rows is when if you're farming on a hillside, you make sure to make your rows going across the hillside, not going down the hill. When you make them across the hillside, what that does is it slows down the flow of water. So water cannot move so quickly downhill and start forming gullies and rills and streams and things like that. Another thing you can do is plant cover crops. So it's always a good idea to never leave the soil bare. When you leave the soil bare, it basically exposes the soil, the topsoil, to removal from wind and rain, right? So when the raindrops impact the soil, it breaks up the soil. So what you want to do is maybe in between crop seasons, you can plant something to cover it up, cover crops, and that will keep the soil protected from erosion. Another thing you can do is planting windbreaks. Now this picture you see here is very extreme, but it is very common to plant windbreaks around farms to, again, prevent soil erosion from the wind. You want to try to retain topsoil as best you can, because that contains all of the organic matter and all of the nutrients that are, not all of it, but a lot of the nutrients that the plants need to survive. So anyway, hope you enjoyed the lecture for today. Hope you have a good week, and I will talk to you next time when we go over streams. So see ya then.